Repeaters, bridges, and switches. The module covers the concept of extending the distance across a local area network. We will cover the physical devices, repeaters, bridges, and switches, plus discuss the spanning tree protocol. Our final topic will be a description of virtual switches used in a local area network. Distance limitation is a fundamental part of LAN designs. When designing a network technology, engineers choose a combination of factors that can be achieved at a given cost. These factors include capacity or the required bandwidth, how much the delay can be tolerated, and distance the network spans. Hardware is designed to emit a fixed amount of energy, and if wiring is extended beyond the design limits, stations will not receive a sufficiently strong signal and errors will occur. A maximum length specification is a fundamental part of LAN technology. LAN hardware will not work correctly over wires that exceed the bound. Extension mechanisms do not increase the signal strength, nor do they merely extend cables. Most mechanisms used to relay signals across longer distances use a standard interface and insert additional hardware components. The simplest LAN extension mechanism consists of an optical fiber and a pair of fiber modems that are used to connect a computer to a remote Ethernet switch. The figure illustrates the interconnection. Each of the fiber modems contains hardware to perform two chores. First, to accept packets over the Ethernet interface and send them over the optical fiber. And secondly, to accept packets that arrive over the optical fiber and send those packets over the Ethernet interface. A pair of fiber modems are used to provide a connection between a computer and a remote LAN, such as Ethernet. In practice, implementations use a pair of fibers to allow simultaneous transmission in both directions. This setup is common for local area networks that exceed the 100-meter limitation of twisted pair cabling. A repeater is an analog hardware device used to extend a local area network. The repeater amplifies and sends all incoming signals to the other side and sits at layer 1. It does not need to understand the commands. It merely transmits a copy of the signals that arrive at the removed sensor. So this analog device is used to propagate LAN signals over long distances, and it does not understand packets or signal coding. Its only job is to amplify the signal and transmits the amplified version as output. A repeater was used extensively with older versions of LAN technologies. Recently, repeaters have been introduced with infrared receivers that permit a receiver to be located at a longer distance from the computer or control device. Consider a situation in which the infrared receiver for a cable television controller must be in a different room than that controller, such as in a sports bar. A repeater can extend the connection as shown in the figure. A bridge is a mechanism that connects two local area network segments. A bridge works by listening in promiscuous mode on each segment. In an Ethernet LAN, promiscuous mode is a mode of operation in which every data packet transmitted can be received and read by a network adapter. When the bridge receives an intact frame from one segment, it forwards a copy of the frame to the other segment. When two LAN segments are connected by a bridge, they appear to behave like a single LAN, and any computer connected to either segment can send a frame to any computer on both segments. For instance, a broadcast frame sent on either segment will be delivered to all computers. Computers do not know whether they are connected to a single LAN segment or a bridged LAN. The figure illustrates the conceptual architecture. A bridge is a mechanism used to connect two LAN segments and forward frames from one segment to another. Computers cannot tell whether they are on a single segment or on a bridge's LAN. Bridge technology is incorporated into other devices such as a cable modem or DSL modem. Bridges do not blindly forward a copy of each frame from one LAN to another. Instead, a bridge uses MAC addresses to perform filtering. The bridge examines the destination address in a frame and does not forward the frame onto the other LAN segment unless necessary. The Ethernet frame is preceded by a preamble and the start frame delimiter, SFD, which are both part of Ethernet packet. The 64-bit preamble is 7 bytes for synchronization, 1010, 1010, and 1 byte for SFD, 1010, 1011, which basically says, here comes a new frame. We were not able to view the preamble in Wireshark since it gets stripped at L2 before Wireshark can look at it. The next field is the destination MAC address, followed by the source MAC address. The ether type is used to tell the device how to process the frame. The payload is the information supplied by upper layers of the TCP/IP model. And the CRC is used for error checking. The CRC is referred to as the FCS or frame check sequence. If the LAN supports broadcast or multicast, the bridge will forward a copy of each of the broadcast or multicast frame to ensure that the bridged LAN operate like a single LAN. So how can a bridge know which computers are attached to which segments? Most bridges are called adaptive or learning bridges because they learn from the locations of computers automatically. To do so, a bridge uses the source MAC address field found in the layer 2 frame to know where to send the packet. When a frame arrives from a given segment, it extracts the source address from the frame's header and adds the address to a list of computers attached to the segment. The bridge must then extract the destination MAC address from the frame and use the frame address to determine whether to forward the frame. A bridge learns that a computer is present on a segment as soon as the computer transmits a frame. Consider the table that lists a sequence of packet transmissions in the event column. The location of the accumulated device information is contained in the segment 1 and segment 2 columns, and the location of where the packet is sent is found in the frame sent column. Bridge extracts the MAC address from the source address field in the frame and adds computer A as part of segment 1 to its table. When B sends a packet to computer A, the location of both computer A and computer B is now listed at the appropriate segment interface. An adaptive bridge uses the source MAC address in a packet to record the location of the sender and uses the destination MAC address to determine whether or not to forward the frame. A bridge network can exhibit higher overall performance than a LAN with all devices connected to one hub. This is because a bridge permits simultaneous transmission on each segment. Using the figure, you can see that computer A can send a packet to computer B, while at the same time computer X sends a packet to computer Y. Although the bridge receives a copy of each packet, it will not forward either of the packets because the destination is located on the same segment as the source. The bridge merely discards 2 frames without forwarding them. Because a bridge permits simultaneous activity on attached segments, a pair of computers on one segment can communicate at the same time as a pair of computers on another segment. The figure shows 4 LAN segments currently connected by 3 bridges with a 4th bridge about to be inserted. Assume the computers shown in the diagram are also plugged into each of the hubs. We will trace a broadcast packet through this network, first without the 4th bridge attached, then with the 4th bridge attached. Hub 1 sends a broadcast packet. Bridges respond by sending a broadcast packet out each interface except the one it can in 1. The packet is sent to bridge 1, who sends it to hub 2, sent to bridge 2, sends to hub 3, to bridge 3, to hub 4, to bridge 4 and hub 1. Sends the broadcast packet to bridge 4. Since bridge 4 only connects to hub 1, bridge 4 does not forward the packet. Before the fourth bridge is inserted, the network operates as expected. Any computer can send a unicast frame to another computer or broadcast frame to all computers successfully. Note, when bridge 4 is connected to hub 4, right here, the process of sending the broadcast packets continues repeatedly until all resources are used, creating a broadcast storm that ends in the network crashing. However, when the fourth bridge is connected to hub 4, right here, a problem arises because a loop now exists. Click through the PC sending packet to hub 1 sending to bridge 1, and bridge 4, etc. 11 produces a broadcast storm. Before the fourth bridge is inserted, the network operates as expected. Any computer can send a unicast frame to another computer on a broadcast frame to all computers successfully. When a fourth bridge is inserted, a problem arises because a loop exists. Unless at least one bridge is prevented from forwarding broadcasts, copies of a broadcast frame will continue to flow in a cycle forever. This broadcast storm will continue until all resources are depleted and the network crashes. To prevent packets from cycling through the network, a distributed spanning tree protocol is used. In a DST, the algorithm views bridges as nodes in a graph and imposes a tree on the graph. A tree is a graph that does not contain cycles or loops. The original protocol, DEC, in 1985, was designed for Ethernet networks and known as Spanning Tree Protocol, STP. STP consists of 3 main steps. First, a root bridge is elected. All bridges multicast a packet that contains their bridge ID, and the bridge with the smallest ID is chosen. A manager can control the election of the root bridge. A bridge ID consists of 2 parts, a 16-bit configurable priority number and a 48-bit MAC address. The network manager can assign a priority number to ensure election of a specific bridge. Next, the shortest path computation is accomplished. Each bridge computes the shortest path to the root bridge. The links included in the shortest paths of all bridges form the spanning tree. Lastly, the forwarding process begins. An interface that connects to the shortest path is enabled for forwarding packets, and all other interfaces are blocked. In STP, Ethernet bridges communicate amongst themselves using a multicast address that is reserved for STP. Step 1. Bridges multicast a packet that contains their bridge ID, and the bridge ID with the smallest ID is chosen. Step 2. Each bridge computes a shortest path to the root bridge and designates ports, user traffic on non-designated ports. And finally, step 3, the bridges begin forwarding packets. First images shows the network with all interfaces open, and on click, the second image displays the blocked port and spanning tree protocol has been run. Variations of STP were designed and standardized. In 1990, IEEE created a standard named 802.1d, which was updated in 1998. IEEE standard 802.1q provides a way to run STP on a set of logically independent networks that share a physical medium without any confusion or interface. Cisco created a proprietary version of STP, per VLAN spanning tree, also known as PVST, for use on VLAN switches. IEEE standard 802.1w introduced the rapid STP and has been incorporated in 801.1d-2004 in 1998 and now replaces STP. Two versions of RSTP are multiple instance STP and multiple STP. These handle more complex VLAN switches and provide redundancy in order to prevent the single point of failure.